I'd like to introduce the next speaker, Tuomas Virtanen. He's a professor at Tampere University, Finland, where he's leading the audio research group. He has also been working as a research associate at the Cambridge University Engineering Department, UK. He's known for his pioneering work on single-channel audio sound source separation. His research has been recognized by many Best Paper Awards. He will be giving a talk today on the spherical audio-visual learning. Take it away.
Great. Thanks. And hello, everybody. It's my pleasure to be in this workshop. Very interesting talks. So, okay. The title of my talk is Spherical Audio-Visual Learning. I don't think this kind of term hasn't been much, so maybe I need to explain a bit. Okay, so what I want to basically do is, this is about using spatial information in audio-visual learning, and more specifically, for example, covering the whole sphere around some capture device and using high resolution. And unlike most of the other talks, they presented some results, so this is actually some ongoing work and mostly about some ideas I would like to work on. So I'm hoping to kind of get you excited about this and share some kind of perspective and ideas. So, and if anybody is interested in collaboration, so I'm actually working on these topics. Okay. So let's see, what's the starting point for this? So I will first discuss some shortcomings of some what has been done in the past. So if you think conventional audio-visual learning, the setup is typically such that there is image or video and the corresponding audio. And for example, this is the basic setup that is done in this kind of cross-modal self-supervised learning. And obviously we know there is some limitations. Okay, some assumptions there is that there is some kind of association between the images and video and the audio. But obviously in the video, for example, there is many visual objects that do not produce sounds. For example, the buildings over there, the humans do not make their sounds all the time, and traffic lights make beep only sometimes. And on the other hand, in the audio, there can be some sound sources that are outside of the visual view there. So it's not really perfect association. Okay, this self-supervised learning techniques seem to work, at least, even though there is this kind of mismatch. But let's think a bit what we could do better to deal with this mismatch, and how could it help in doing better audio-visual learning. So okay, I'm going to focus on the spatial properties of audio and video in this talk. Okay, so in case of images or video, okay, so there is very clear and explicit correspondence between spatial information and the actual data. So if you position some video camera to some scene, and then they take video, then one pixel in the video, of course, corresponds to one spatial angle. So that's very clear. On the other hand, most of the material that is used in audiovisual learning uses this kind of narrow field of view. So there is many things outside the field of view. Then on the other hand, if we consider audio, most of the work is single-channel audio, and okay, like Josh said in his presentation, like in audio, the spatial information is really no explicit. And if we just use one basic microphone like this on the figure, you basically don't have any spatial information, so no idea where the sound sources are. Of course, like we have been seeing today, it's possible to use, for example, stereo microphones, which helps you to get some idea if things are on the left or right or so. And in ideal scenarios, for example, if there is no noises, you can even get pretty good localization. But in realistic scenes with multiple sources, it's quite limited what we can do with 2 microphones, for example. And one important property in audio is that basically the signal that is recorded, it's a superposition of all the sources that are present in the scene. So basically what you are recording is acoustic mixtures. So, whereas in vision, if you think, well, 1 pixel almost always corresponds to 1 visual object. But in audio, if you think some data, it's consists of multiple sound sources. So in case of audio, if you think when you are doing some cross-modal learning, you're actually dealing with this kind of mixtures of things instead of isolated sources. Okay, so there was some in the introduction talk, in the first one today, there was discussion that there is some object-level audio-visual learning, but I'm kind of inclined to claim that actually it's based on whole scenes when there is multiple sound objects at least, and I think this is then very likely to introduce some sort of biases of course in the data sets there is lots of biases, but then so we end up then learning things that are not about the sources themselves, but some kind of latent things related to whole scene. Okay, so my main point here is that in most of the conventional audiovisual learning, there is mismatch between the spatial information in the visual data and audio data. Okay, I guess you can maybe see where this is leading. So of course you know there is 360 cameras that we can use to capture the whole visual view, and we can basically use that to fix the problem with the limited field of view in images or video. Okay, what can we do with audio? There has been talk about microphone arrays, but not yet much about spherical microphone arrays. I don't know how well they are known in the vision community, but basically they are this kind of devices, well, typically, as the name says, kind of shape of a sphere with multiple microphones on them. And here I'm talking really then significantly larger number of microphones that has been discussed so far. So for example, tens of microphones. And those can be used to get then better spatial resolution in localization, source separation, and this sort of things. And okay, okay, you have all seen 360 videos, but I will just play this quickly. So this is related to the, because I'm on some demonstrations using this video over here. So this was shot last year when there was still lots of coughing around. So people, these are students wearing masks, so they don't look very happy, even though we gave them some movie tickets to participate this kind of recording. But anyway,
maybe we
can you turn up the volume a bit?
Yeah. Everything together. Yeah.
Okay. Yes. Okay, so what you can do then with, if you capture then a 360 video and audio with spherical microphone array. So for example, then you can estimate from which direction the sound energy comes from. What is done here is that we basically make some beamform into different directions and estimate how much energy there is from each spatial angle, and then overlay this kind of heat map on top of the video. So then we get visualization like this. Maybe so there is the air condition on the top, and then female speech, male speech, and then these musical instruments. Okay, so you can get kind of information like this. And you may have seen, for example, acoustic cameras. There is, for example, videos of those on YouTube. So this is not a new thing. But what they typically do is they simply analyze the energy of the sound coming from different directions. But with the spherical microphone array, when you do beamforming, basically filter the sound from specific direction, you get the acoustic signal as well. You can calculate the spectrogram and do learning based on those. This hasn't been really done yet. Okay, so okay, I have mentioned spatial. Okay, for the people that have been working on vision, I will maybe briefly explain where microphone arrays in general are being used. So spatial filtering, sound localization, and obviously capture and reproduction. So maybe let me show one video related to localization, because actually joint localization and recognition of sounds has become very hot topic in the audio domain. So we have been, actually this data that I'm showing was kind of primarily collected for that kind of purposes. So then if you localize sounds and then recognize them, then you can get visualizations like this. So there is now some tags of classes overlaid on the video. And you can see the resolution of the video is bad. It was not originally, but when we rendered the video with the labels, that's what you get when you when an audio guy tries to do this video rendering. So, but yeah, okay. Maybe another example, a bit more lively talk there. So this is now with human speakers.
So how's the life? Life? Well, it's a bit busy recently. Okay. Because yeah, I was just moving. Like the weekend before, I was in Tallinn.
Yeah, I saw your picture on Instagram.
Yeah, yeah, not on Instagram, on Facebook. I don't have Instagram.
Okay, so I misunderstood.
Yeah.
Okay. Then about spatial filtering. So what's the point? I think here I can talk a bit. What's the point if in using then a microphone array with large number of microphones in comparison to, for example, just a stereo microphone or then 4 microphones. So this figure here shows the beam patterns. What we have there in the left is the response, this kind of beam pattern if you have 4 microphones. So this is kind of this first order ambisonics capture. So okay, you can more or less filter sounds coming from the left or right, but not spatially very accurate. And there what we have there in the right is then this filter response, spatial response, if we have 4th order ambisonics. So that's then 25 microphones. So much more narrow spatial beam there. And yeah, if I, okay, this is then video where we have then filtered the sound of Kantele. So that's the instrument over there. Okay, where is my cursor? No, it's not visible there. I need to show from here. Okay, there, it's there in the left. And so in the previous videos, you heard quite some noise, for example, from the ventilation. So it's mostly gone. The female voice is gone, and so on. So this is very. You don't hear yet anything because other things have been filtered out. You can hear a bit the xylophone. But the focus is now in Kantele. And this is with a static beamformer. So basically, if you do adaptive beamforming, which then actively tries to then cancel the other sounds, you can get, I would say, almost perfect isolation of sources that you are interested in. Okay. So how do you get data to, I mean, if you want to do audio-visual learning with material like this, how you can get material like this? So there is some integrated devices which have a 360 camera and spherical microphone array, but they are not very common yet, and in those of that are available, the number of microphones, for example, is still quite limited. So for example, in the experiment that we have been doing in my group, we have been using Eigenmic, which has 32 microphones, and then Ricoh Theta for 360 video capture. So of course, like for the video, there is much better devices available, but we just use this one because it's relatively easy then to mount these two, for example, on top of each other, this almost kind of aligned capture in space. And we have been collecting then data using this kind of capture setup. And we have published in total 7 hours of material collected with this setup, and this was done in collaboration with Sony. So there is recordings done in Tampere by my group, and then in Tokyo by Sony. And this data set that we have released, it was meant originally for sound localization research. So John was mentioning that there is not so many realistic data sets available, so then here is one that you can consider using. So what we have released is then recordings where we have 4 channels in microphone format, so picking microphones from this among these 32, or then first order ambisonics, which is then the spatial representation of this these captures. And we are going to actually release soon this full 30-channel audio plus the 360 video as soon as we are able to make blur the faces on the video. So again, for an audio guy that takes a bit some time, but by the end of this year, I promise that we will do it. And there is the Renodo link from which you can already find this 4-channel recordings. And since this dataset was collected for sound localization research, we have also spatiotemporal annotations of sound events from 13 classes. So basically locations where the sound sources are, and then when the sounds are active, and when they are moving in time also, then the time varying locations, and then annotations of these 13 classes. And okay, let me quickly explain how we actually were able to collect this location information. And okay, first of all, obviously, because if you record audiovisual material, you have and you want to make it publicly available, you have of course problems with privacy. So what we did, we then recruited students to come at the university to participate in the recordings. They give the permission. And then for the localization, we actually used the OptiTrack motion capture system to get automatically the locations. And then also we closed mic'd all the sound sources to get kind of semi-automatically the activities of the sound sources. So this was basically the hardware that we used. So record data for the video, then EigenMic for audio, then this OptiTrack for motion capture, and then this closed mics for source activities. So this was basically the setup. So we set up the OptiTrack around some rooms, and then EigenMic and record data in the center, and then the actors were doing things in the rooms. And then all the sound sources, they had this kind of visual markers for the tracking. This is Parta who was doing most of the recordings, so did lots of work. And we did the data collection in different locations at the university because it was just easy to carry the equipment to different places there. And from this closed mic recordings, they are visualized over there. We can actually publish also those. This can be very useful for sound source separation research. So far we have been using them only to basically the activity of the sound sources kind of semi-automatically with some manual corrections. And then you get data like this, what I already showed here. So the locations of the sound sources and tags for each of them. Okay, so what can you do with this kind of data? So of course, with like I said, if you have a spherical video and audio, then you get really matching spatial coverage. Of course, the resolution in the audio, spatial resolution in the audio is not still the same as in video, but much better than what you have, for example, with stereo microphone or 4 microphones or things like this. So the point, I think the main benefit is then is the high spatial resolution, because if you have 32 channels, you can do very selective spatial filtering, and that allows you to focus, for example, audio-visual learning, instead of the whole scene of acoustic mixtures to individual sources that you have. So you can filter that in this spatial location there is the dog barking. You can filter the dog barking and then do cross-modal learning more effectively. And of course, now since you have more accurate spatial information, you can also get dynamic information when sound sources are moving. And that's also beneficial in the sense that often when there is something moving in a scene, that also often produces a sound. So some kind of activity or movement is typically an interesting cue in audio-visual learning, which hasn't been utilized that much yet, I would say. Okay, so where you can do this. Representation learning has been mentioned already several times in this talk and the previous ones. So basically, what I already said. So from scene level representation learning to individual objects, but also now with this high spatial resolution recordings, you can do also new things. So for example, in representation learning, for example, predicting some missing information is often done. Now you can do the same thing with spatial audio. So for example, if we remove some spatial information, how you can predict that. Or then do spatial augmentation. So you can learn some audio-visual models. So of course, then this kind of spherical microphone arrays are a bit inconvenient to do kind of capture in some scenarios. But you can use this kind of audio-visual material to learn some audio-visual correspondence, and of course then use, for example, if you have a video capture and just mono audio, then to do spatial augmentation. And this kind of material will help then, like we did here, we generated basically automatically material for sound source localization. So having then audio-visual spherical data allows you to generate much more training data for many kind of established tasks. There is still some open questions here, which need to think some thinking how to exactly solve them. So for example, when doing representation learning, so in videos, the spatial information is really explicit, but in audio is not. We have the microphone signals or then we have the ambisonics recordings, but anyway, the one audio recording, one channel doesn't correspond to one spatial location. How to deal with this is, for example, that we can do some beamforming, so basically spatial filtering on some predefined grid. So filter audio coming from some predefined locations and use those for learning. Or maybe if we want to do it a bit more cleverly, we can localize where the sound sources are and then focus the filtering on those. I think both ideas should be tried out. Then regarding room responses that have been discussed so far, so that's something that needs to be taken into account. So, okay, if we consider a scenario where there is a speaker in a room, there is the direct sound from that speaker to the microphone array, but also the reflections. And now if you think the sound, okay, if I consider the sound coming from that direction, okay, what I see there is only a wall, but when I'm talking like this, there is actually my voice, which is reflected from the wall. And if you do, then if you now have a kind of high-resolution spatial audio, you need to take this into account because there is my voice also coming from other directions. So in addition to the, and if you're using kind of audio-visual correspondence learning, like how you take into account these directions where I don't exist. And okay, if I play quickly this video, this is now with more high-resolution beams, so we can actually see from there some reflections there in this room. Luckily, there is some signal processing solutions that we can use here, for example, to extract only the direct path and eliminate the reflections. So yeah, there is good potential what can be done there. And okay, then the third open question, which is maybe a bit more broad, and I don't have yet so many ideas how to deal with that, is related to the radiation patterns of the acoustic sources. So what does this mean? So I think this relates to the broader concept of kind of semantics in audiovisual learning. So again, if I think about self-supervised learning, I think behind there is some ideology that in audio and video there is some similar association between the semantics. So okay, let me explain what I mean by this. So if we think the concept of a car, so okay, first the visual concept of a car. So okay, we know cars are some metallic boxes like this. They have windows and four wheels and lights and something like that. And okay, if we think then the semantics of sound object of a car. Okay, we know cars make sounds or some types of sounds, and okay, we can mentally associate this visual and sound image. But actually, if we think the acoustic source, the sound of a car is not coming from that metallic object, the whole metallic object. It's mostly coming from the wheels and the engine. It depends on the speed of the vehicle and for example, what kind of engine it has. So there is difference in, for example, what humans associate. Okay, I think we humans associate, if you think the sound of a car, you associate to the whole object, but not really thinking explicitly that the sound is coming from the wheels. And when you start doing then kind of high resolution correspondence learning, then you need to take these kind of things into account. Of course, you can play around with the resolution, and then you may not have these kind of problems. But I think this is, for example, related to semantic segmentation. So interesting things that can be done related to this idea. Okay, I think I have used most of the time, so I can maybe just mention briefly that this was assuming, I mean, the data collection, for example, that we had was based on kind of static capture devices. Of course, you get some challenges if you want to work with egocentric capture or then multiple distributed devices, but I think there is lots of potential over there. Of course, I didn't do this research myself, so especially data collection, there was many people in my research group helping, and from Sony they also contributed significantly. And related to this spherical audiovisual learning, so I was mostly presenting ideas originating from collaboration with Argontis Politis and Esa Rahtu and Toni Heittola in my group, and Shinji Watanabe from CMU. And thank you. There is still the link to the dataset if you are interested in trying that out.
Does anyone have questions?
Yeah, thank you. Very interesting talk. Particularly excited to see that you collect data for 3D vision and 3D audio. I think it's something that's just being ramped up, and it's very exciting that there's a public data set. One question regarding, the scalability of this data captures. Like any capture device that we have in a room, cameras, etc., none of them are acoustically transparent, right? And I've seen that you also mounted the 360 camera right over the microphone array. So it will kind of interact with the microphone itself. Where do you see limitations? How much, visual devices can we realistically bring into such a capture before the audio data will be too corrupted to be useful?
Very good question. I'm not maybe an expert to answer this. Well, there are some commercial devices, basically integrated devices which have, for example, this kind of sphere shape, where there is microphone cameras and microphones on top of a sphere. And I think if you do it like that, then I think this eliminates many of the problems. But then I think those are mostly this kind of static capture devices. So if you really want to get to, for example, egocentric capture, there has been, for example, with some glasses or other devices, you are going to have, some sort of limitations. So I think then there is questions how you can, okay, then the microphone array is definitely not a spherical one. But of course, you can still use microphone arrays like this to do many of the things that I presented here. Of course, it affects, for example, the spatial resolution. So it will be better in some parts and some not. But yeah, I don't really have a kind of complete answer to this, but maybe these are some ideas.
Cool. Anyone else? If not, I'll have a question myself. So for the emisonic microphones, I wonder if it's possible to predict the depth information, because like for the 3D, the panorama image you were showing, you were only plotting like the heat map on the 2D image plane, right? I wonder like if it's possible to do like 3D sound localization with the emisonic microphone.
Yes, good question. It is possible to some degree. So, for example, in my group, we have already been doing some rough localization of the distance, but it's much more limited what can be done. So, of course, if you have distributed microphone arrays, then it becomes more feasible. But with one localized microphone array, it's definitely more challenging. I think if you can train specific model for one room and use the reflections, then it's or if you can afford to move in the room to get more spatial cues, then it becomes more feasible. But if it's just a static microphone array, then I think you are limited to very rough distance estimation. So just close or distance or something like that.
All right. If no other questions, let's thank him all. Thank him again for the great talk. Thank you.
Thank you.